All right, so this is section 5.6, rational functions. So luckily this is stuff that you've already seen in Algebra 2, but this will just be a quick overview. So by definition, a rational function has a variable in the denominator. So recall in chapter 3, we learned about these toolkit functions that are shown here in the graphs, the reciprocal function here and the reciprocal squared function. And so two important features of a rational function are vertical asymptotes and horizontal asymptotes. And so vertical asymptotes look like this. So they're, we have this imaginary line where the function doesn't cross. And so notice both of these have a vertical asymptote at x equals 0. So I'll just notate that there. And then we also talk about horizontal asymptotes, which I'll denote in blue. And those are kind of where the graph approaches horizontally, and we denote those y equals a number. In this case, y equals 0. So those are the, we abbreviate these HA for horizontal asymptote, and for vertical asymptote, we just denote those BA. It's just much easier than writing out all of that. So when you see that in the future, that's what I'm talking about. So we also learned earlier in this chapter about the end behavior of polynomials. And so we also have end behavior for rational functions. And so let's talk about that here. So remember the end behavior is what happens as the x values get really, really large to the left and as they get really, really large to the right. And so we write that in arrow notation. So for this first function, the reciprocal function, as x approaches negative infinity, y is approaching, and that's remember vertically. So as we move this way on the graph horizontally, what is the graph doing vertically on the left-hand side? And so that it's approaching 0. It's approaching that horizontal asymptote right here. So y is approaching 0. And as x approaches positive infinity, we have y also approaching 0. So that's something important about a rational function, is if there's a horizontal asymptote, the end behavior is going to kind of follow that. And so as we saw previously, we have another horizontal asymptote here, which is 0. And so that end behavior is going to be very similar for the reciprocal squared. So this is going to be as x approaches, that'll be negative infinity, right? Y again approaches 0, and as x approaches positive infinity on the right-hand side, y is again approaching 0. And so just as a reminder, this is towards negative infinity and positive infinity. Those are horizontal, and vertically, we're talking about that y value. So in addition to the end behavior, we're also interested in the local behavior. And what that means is towards the middle of the graph, really. So the local behavior is kind of happening at the vertical asymptote. So remember, we have a vertical asymptote here, and that's x equals 0. So let's talk about local behavior. And since we're not on the left-hand and right-hand side of the graph, we need to really hone in on what the x value is approaching. So we're still going to have as x approaches a value, but we're talking about the local behavior, which is what is happening around this region of the vertical asymptote. So in this case, x is approaching. Let's look from the left. So let's look at 0 from the left-hand side. We'll say 0 from the left. So as x is approaching 0 from the left, and that's how we denote that. From the left is going to be that negative sign because it's coming from the negative direction. Y is approaching. So if you look, it's approaching, it's going down infinitely. So y is in fact approaching negative infinity in this case. And now we need to look at as we approach 0 from the right. And so if we use negative to denote from the left, we're going to use positive to denote from the right. So as x approaches 0 from the right, what is the y value doing? And we can see that as we approach from the right, it's going positive infinitely. So that's going to be at positive infinity. So this is the local behavior. So if you want to try to use the arrow notation to describe the end and local behavior for the reciprocal squared function, go ahead and give that a try. And pause the video and see how you do. All right, so as x approaches negative infinity, y is approaching 0. And as x approaches positive infinity, y is approaching 0. That's the end behavior. And then the local behavior is as x approaches 0 from the left, y approaches infinity. And as x approaches 0 from the right, y is also approaching infinity. So moving on, applied problems with rational functions. In general, we use related rates or concentration problems. So if you want to take a second and pause the video and read this paragraph so you can kind of follow what I'm talking about, that would be extremely helpful instead of me just reading it to you. All right, so hopefully you've read that. And so you see that we have, it's asking about the concentration of sugar in the water. And it's asking, about the difference between the initial, concentration and the concentration after a certain amount of time. So, of course, we probably need to figure out the initial concentration first, and that's going to be the amount of sugar per the amount of water. And so the initial concentration, it says that we start with 5 pounds of sugar and we start with 100 gallons of water. And so as a decimal, we can find that that is 0.05 pounds. I just literally wrote it libs. Goofy. Pounds per gallon. Make sure you use the correct units here. You just divide these units to get these. And then the next part of what we need to do is we actually need to write a linear function that relates how the sugar and the water are changing over time. So we have, remember, we write the initial value plus the rate times the time. So the sugar is pouring in at a rate of 1 pound per minute. So we start at 5 and it's 1 pound per minute. And then for the water, we start at 100 and we're pouring in 10 gallons per minute. So this would be 10 times t. And so this is just a y equals mx plus b linear function. And so this is the function that describes the concentration, c, as a function of t. And so this is going to be our rational function that describes the concentration over time. And so what it's asking us is to figure out how much the concentration is after 12 minutes. So that means that t equals 12. And so all we have to do is come over to our function and plug in 12, find c of 12. And so that'd be 5 plus 12 over 100 plus 10 times 12. And we would obtain, 17 over 220, which simplifies to 0.08 pounds per gallon. And we can see that the concentration is in fact greater. So concentration is greater after 12 minutes than it was initially. So greater after 12 minutes. Okay. So if you want to try one of those, this is a similar problem, just with different, instead of sugar and water, we're talking about first year and second year students, but you'll set that up the exact same way. So if you want to pause and give that a shot. All right, so you should have found that this was a ratio of 12 to 11. And so now let's talk about finding the domain of a rational function. Hey, we've done this in chapter 3. So to find the domain of this, remember, we need to determine what inputs x would result in division by 0 and exclude those from the domain. So that means that I need to know where the denominator is equal to 0. So I'm going to solve for that. And I'm going to do that by factoring this as a difference of squares. And so that's going to be x equals 3 and x equals negative 3. And so we'll say that the domain is all real numbers except x equals 3 and x equals negative 3. So that's just a quick review from chapter 3. So if you want to try one real quick, see how much you remember, because we're going to need this skill. So you should have found all reals except x equals 1 and x equals 5. All right, so the next topic is identifying vertical asymptotes of rational functions. And so vertical asymptotes basically describe the behavior of a graph as the output gets really, really large or really small. And so to find those vertical asymptotes, we just need to determine where the denominator is equal to 0. And so here are a set of steps to do that if you need to refer back to it. So the first thing we want to do is we want to factor the numerator and the denominator. And so I'm going to assume that you become pretty proficient at factoring. And so I'm just going to go ahead and write the factored form of the bottom. And so you should have obtained x minus 1, x plus 2 as a denominator after factoring it. And we want to cancel any factors that cancel, and none do. So then we just want to figure out where the denominator is equal to 0, because those asymptotes occur where the function is undefined. And that's where the denominator is 0. So we'll find that that would be at x equals 1 and x equals negative 2. And so that's where your vertical asymptotes will occur for this function. And you can see here that this is a graph of the function that we just analyzed. And so here's one vertical asymptote and here is the other. Okay. So now let's talk about removable discontinuities. We call these holes also. Basically, it's a single point where the function is undefined rather than an entire asymptote. And so the process is the same. You take this function, you factor the top, you factor the bottom. We see what cancels out. Now, whereas the vertical asymptotes are obtained where the denominator that doesn't cancel is equal to 0, so that would be at x equals 3 for your vertical asymptote. The hole or removable discontinuity is obtained from the factors that do cancel. So this would be x minus 1 equals 0, meaning that we have a removable discontinuity. So that should be plus at negative 1. And so, again, that's the difference. Where it cancels gives you the hole or removable discontinuity, and where it does not cancel in the denominator is going to give you that vertical asymptote. So if you want to give that a try, find all vertical asymptotes and removable discontinuities in this example and see how you do. All right, you should have found that there was a hole at x equals 5. And there was a vertical asymptote at x equals 0 and x equals 1. One quick note, if you want to find so the hole is actually a single coordinate. So if you want to find the y coordinate of a removable discontinuity, you're just going to take this x and plug it back into the function that was left over after canceling the factors. So we're going to plug in the negative 1 to this. So that would be negative 1 minus 1 over negative 1 minus 3. We would see that the y coordinate for this removable discontinuity would be 1/2. And so that gives us, instead of just the x value, gives us the full coordinate location. And so from there, we're going to identify horizontal asymptotes of rational functions. And so horizontal asymptotes describe the behavior of the graph as the input gets very large. In other words, the end behavior. And so we learned earlier in chapter 5 that a polynomial end behavior depends on the leading coefficient. And because here we have a fraction, it's going to be the ratios of the leading coefficients. So there are 3 specific cases that we can encounter. Case number 1, the degree of the numerator is less than the degree of the denominator, and in that case, you're going to have a horizontal asymptote at y equals 0. And so notice this is degree 1, this is degree 2. It's bigger on the bottom, so that's a y equals 0 horizontal asymptote. In case number 2, the degree of the numerator is bigger than the degree of the denominator by exactly 1. So this is a degree 2, degree 1, and you're going to have to find what we call the slant asymptote. There's not even a horizontal one, it's a slant asymptote. You can see a picture of it there, of what that looks like, using division, right? So you can use any division method that you're familiar with. In this case, I'm going to use synthetic, just because, why wouldn't I? Because that's pretty simple. So this would be 3, 3, 1, 1, and 2. And so then the quotient is actually going to give me the slant, and we ignore the remainder. And so this is going to give me my slant asymptote. And then finally, case number 3 is where the degree of the numerator is equal to the degree of the denominator, in which case we take the ratio of the leading coefficients, which would be 3 and 1. And so this is going to be y equals 3 for our horizontal asymptote. So you'll be responsible for memorizing those 3 cases. Example 5, let's identify all non-vertical asymptotes. So here, notice I have equivalent degrees. And so the horizontal asymptote will be located at the ratio of the leading coefficients. So that'll be y equals 3. Here we have the degree 1 larger in the numerator, so we will need to divide to locate the slant asymptote. Because there's not a horizontal, it is a slant, so that'd be -4, 1. By synthetic division, this would be -2, -6, +12. I don't even care about the remainder. It doesn't even matter, because for the slant asymptote, I don't even need it. And so in that case, I would have x -6 as my slant asymptote. So we'll abbreviate that SA. And then here I have the degree 1, I have the bottom degree larger, so that's going to be a horizontal asymptote at y equals 0 automatically. So example number 5, identifying non-vertical asymptotes again, and then we're going to actually apply this. And so the non-vertical asymptote in this case is a horizontal asymptote. And so if we rewrite this in the proper format so we can easily see the leading coefficients, we'll see that the ratio of the leading coefficients is 1/10. And so we're going to have a horizontal asymptote at C of t equals 1/10. And what that means that as time goes by, the concentration will approach 1/10 pounds per gallon. Or you could also say 0.01 pounds per gallon, whichever is your preference. I'm okay with whatever. All right, so in example 5, we'll identify all of the asymptotes. And so I've already factored this for you. I may ask you to factor it in a practice problem, but I'm assuming at this point that you can factor this far in the course. So remember, to find the horizontal asymptotes, we compare the leading coefficients, which would be our A values. Here they're the same. Actually, hold on. Don't make the same mistake I did. We want to compare the degrees to see what we need to do. This is degree 2 because there are 2 x's. This is degree 3. So the degree is larger on the bottom, so the horizontal asymptote will be located at y equals 0. And then in order to find the vertical asymptotes, we're just going to see where the denominator is equal to 0. So that's going to be where each factor is equal to 0. Because none of the factors cancel, so there are no removable discontinuities. So this will be x equals 1, x equals -2, and x equals 5 for all of our vertical asymptotes. If you want to give it a try, locate all vertical and horizontal asymptotes of this example. And you'd find that your vertical asymptotes are located at x equals 2, x equals -3, and that there is a horizontal asymptote located at y equals 4. By taking the ratio of the leading coefficients. Of course, you'd have to multiply that out to kind of see that. So you'd need to FOIL out these two things on the top and the bottom in order to get that. And then finally, the intercepts of a rational function. So as always, if we're looking for y-intercepts, we just want to calculate f of 0. And the different part is that if we're looking for x-intercepts, we want to find where the function is equal to 0. And so that's just going to be wherever the numerator is equal to 0. So for the y-intercepts, I'll find f of 0. And I'll see that plugging in 0 for x, I have -2 times 3 over -1 times 2 times -5. And so the y-intercept is going to be located at a -3 over 5 or -0.6. And then setting the numerator equal to 0 means I should just set the factors in the numerator equal to 0. And that'll be x equals 2 and x equals -3 for my x-intercepts. And so if you want to give one of these examples a try and come back and see how you did. So you should have found that you have x-intercepts at x equals -2 and x equals 3, and that you have y-intercepts at y equals 3. All right, so make sure that you're prepared to work with some problems on the boards the next time I see you in class, and I hope this helps.